Let's begin with an overview of the typical multimodal RAG pipeline. In general, any RAG pipeline will be comprised of two main phases: the document processing phase and the question answering phase. In more general terms, you can think of them as the data gathering phase and the inference phase. In our case, the document processing phase starts at the reception of the document or set of documents containing the data that will later be retrieved to augment the generation of the LLM. The first step in this process is document layout analysis, or DLA. DLA uses computer vision tools to analyze the spatial arrangement of a document's contents in order to understand its general layout or structure. This allows it to segment the document into coherent units such as sections and subsections with logical components of different natures like paragraphs, charts, tables, formulas, and so on. Typically, in multimodal RAG pipelines, we treat these components as either plain text components on which we perform OCR to extract the text, or we treat them as visual components on which we perform more sophisticated processes to extract the information in textual form. So whether we perform OCR or use image description tools, we turn all the components into plain text, embed them using a textual embedding model, and store them in a vector store. In more sophisticated RAG pipelines, you might want to use different image description tools depending on the specific type of visual data you have, such as models specifically trained on table understanding or chart understanding, and so on. And finally, it's also possible to remove the image description stage altogether and directly use multimodal embedding models on your visual components. We will explore all these possibilities in future videos. The first part of this process was already tackled in a previous video in which we introduced unstructured I/O for document layout analysis and OCR. We will therefore put the focus on the second part of this process, including the image description and textual embedding modules. At the end of the document processing pipeline, our data is now ready to be retrieved and used by LLMs. This is done through what we call the question answering pipeline. For this tutorial, we will explore two main types of inference pipelines in multimodal RAG. Let's call them options A and B. So in option A, we receive the user query. It goes straight to the retriever, which applies textual embedding to the query and performs similarity search on the vector store. This gets us the most relevant chunks from the documents processed earlier. Now these chunks are either plain text or visual elements. If a chunk is plain text, we send it to a VQA chain, which is basically an LLM prompted to answer the initial query based on the chunk of text. If a chunk is an image, we send it a VQA chain, which similarly is a multimodal LLM prompted to answer the initial query based on the image. Now you can think of this entire module as a single unit. It's a branched chain that takes all the retrieved chunks at once, performs question answering in parallel depending on the type of chunk, and finally gets us a set of answers as the output. Finally, we gather all these answers and provide them to a synthesis chain, which is another LLM prompted to synthesize the various answers into one final coherent answer. Of course, here you could ask, why don't we just provide all the retrieved chunks at once to a single LLM and prompt it to directly formulate a final answer? This could be done indeed, and works fine in some cases, but in general, generative AI systems tend to perform best when you decompose LLM tasks into smaller and easier tasks. It helps to prevent hallucination and improve LLM performance in most scenarios. Let's now move to option B. In the same way, we get the user query and feed it to the retriever, who finds the most relevant chunks through similarity search based on textual embeddings. Just like in option A, we are able to retrieve visual chunks through their textual representation in the vector store, which we obtained by performing image description during the document processing phase. Therefore, instead of the QA/VQA branching module from option A, we can simply treat the textual representation as a proxy for the visual chunks. This allows us to send everything to QA chains, which will provide answers either based on retrieved plain text or image descriptions. And in the same way, those answers go to the synthesis chain, which formulates a coherent final answer. As we will see in the following episodes of this tutorial, whether you should choose option A or B entirely depends on the models you have at your disposal. If your model is stronger in image description but weaker in VQA tasks, you're better off with option B, and vice versa. Now that we have a clear understanding of the multimodal RAG pipeline, including the data gathering phase and the inference phase, we can immediately dive into this tutorial and start building the pipeline. we will need to start with a few preparations. First, we have to install the required packages. In our case, it's going to be Langchain OpenAI for interacting with our locally deployed models, and Langchain Qdrant for storing and retrieving vectors. Next, we need to deploy and instantiate the different models we will be using in our multimodal RAG pipeline. In our case, we will be needing a textual embedding model for embedding plain text and image descriptions, an LLM for the QA and synthesis chains, and a multimodal LLM for the image description and VQA chains. For the embedding model, we will be using the nomic model from our previous tutorial. For the LLM and multimodal LLM, we will be using the same model which will play both roles, the Mini CPM version 2.6. Mini CPM version 2.6 is one of the most powerful open-source multimodal LLMs on the market today. It is based on the Qwen 2.7b model and currently surpasses the biggest closed-source models such as GPT-4o and Gemini Pro on the task of single image understanding. This makes it remarkably good at describing the contents of images in detail. If you've been paying attention, you can already tell which one of the two inference pipeline options will work best for us. Just like in our previous LM Studio tutorials, our models are instantiated using the Langchain OpenAI wrapper with the base URL set to our local host. All we need to do now is to deploy the models on LM Studio. So as you can see, the interface has changed since our last tutorial. That is because we needed to install the latest version of LM Studio to benefit from all the new features, supported models, and bug fixes. So make sure you do the same. You can easily find the Mini CPM by jumping to the search engine and simply typing the name of the model. This is the specific version we'll be using in the tutorial. As you can see, we've already downloaded it with the Q5 quantization level, which takes about 6.8 gigabytes of RAM. You can pick any other quantization level if you want to, going down to about 4 gigabytes, and LM Studio will tell you if your machine can or cannot handle it. Once you pick and download your multimodal LLM, you can jump straight to the developer section. Here we can easily deploy our models by simply loading them to memory and starting the server. Let's click on Select a Model to load, and start with our nomic embedding model. If you don't have a GPU, make sure you set the GPU offload to 0 and click on Load Model. Once the embedding model is loaded, we again select our Mini CPM model. Make sure the GPU offload is set to 0, and load the model. While the model is being loaded to memory, you can check your RAM consumption at the bottom right, with respect to the capacity of your machine. Once both models are loaded and ready, all we need to do is click on Start Server. And there you go, both models are instantly deployed and the API endpoints are ready to receive calls. For this to work correctly, make sure you type the LM Studio name for your specific model, which you can get by copying it right here, in the Loaded Models section. And that's it for the preparations. Now we can start building our multimodal RAG pipelines. In this second episode of the Multimodal RAG series, we will build the document processing pipeline and test it on a few examples. As mentioned in the previous episode, the first part of the pipeline was already tackled in our Unstructured I/O tutorial. Tools like Unstructured I/O handle the document layout analysis, OCR, and chunking of document elements. Additionally, they provide screenshots of visual elements which we can then process as separate images. For this tutorial, we will therefore focus on implementing the description chain module and the logic for embedding elements and upserting them to the vector store. So without further ado, let's start building the document processing pipeline. To do so, we will start by building the two main modules, namely the description chain and the vector store. We will then use these modules to build the document processing pipeline and finally run it on a set of sample inputs extracted from a document. Let's start with the description chain. First, we create the description chain using the Langchain LCEL piping logic. For a quick tutorial on LCEL, you can check out our previous video on the subject. As you can see, it is a very simple chain comprising a prompt, our multimodal LLM, and an str output parser to extract the text from the LLM response message. The prompts start with a classic system instruction followed by a user instruction prompting the model to describe the image in detail and extract all data present in it. We then insert our image as a URL containing the base 64 encoding of the image. And that's it. Now we have a chain that we can use to describe any image in detail using our locally deployed multimodal LLM. Let's now test our description chain. So as you can see, we have implemented a function to show the image and another function to call the description chain. This function first encodes the image to the base 64 format, passes it as input to our description chain, and finally streams the output. Let's show our first sample image. As you might have recognized, it's the classic transformer architecture from the Attention is All You Need paper. Let's now see how our chain will describe it. Interestingly, the model also recognizes the transformer architecture from the 2017 paper. It then goes on to describe all the components of the architecture, detailing what happens as the input passes through the left and right side of the diagram. Let's try with a different example, this time with a table, again extracted from the Qdrant paper, which was published just a few weeks ago. And here's the description generated by our chain. So again, it starts with a brief description of the image and tries to infer the subject of the table from its title. It then goes on to convert the contents of the table to a set of rows and extracts all the values accordingly. This basically means that the generated text can serve as a proxy for the table as it contains exactly the same information. This makes it much easier to embed and retrieve the table in a RAG setting. It also makes the question answering phase much simpler too, as the model can directly get the information from the text instead of trying to read a markdown table or an image. Let's now create our Vectorstore module and see how we can populate it with either textual or visual elements. So first, we create a Qdrant collection just like we did in our previous local embeddings tutorial. We specify the embedding dimension, which is 768 for our nomic model, and the distance metric, which in our case is the cosine distance. Next, we create the Qdrant Vectorstore. Again, we specify the model as our locally deployed embedding model, set the collection name to the one we just created, and set the retrieval mode to dense retrieval. Now that we've created our Vectorstore, let's see how we can populate it. So we've implemented this function to upsert elements to our Vectorstore. It takes as input the text and metadata, generates a unique ID, and uses the Qdrant add documents method to push the element to the Vectorstore. In this example, we're pushing a visual element. The text is the generated image description, and the actual image is stored in the metadata as a base 64 string. The function successfully embeds the text, upserts the corresponding vector, and prints its unique ID, which we can then use to delete the vector if we want to. Now that we've built our image description and Vectorstore modules, let's run the entire document processing pipeline on a sample document. So first, we break down the document to a set of document elements. As mentioned earlier, this first part of the pipeline is typically done by using DLA tools such as unstructured I/O, which we've already tackled in a previous video. For this tutorial, we will simply mimic the output of this kind of tools by storing a bunch of elements in our sample data folder. These elements were extracted from the recent Qdrant paper, and as you can see here, we have 4 images and 4 paragraphs. This is the Qdrant paper from which we got those elements. You can see it contains a bunch of images, diagrams, and even tables along with the usual paragraphs. So with DLA tools like unstructured I/O, you typically get outputs like these. Basically screenshots for visual elements and coherent chunks for textual elements. And we get these outputs in the form of dictionaries containing the type and contents of the element, and where images are already in base 64 format, which is what we're mimicking with this for loop. Additionally, we implement this function to help us visualize our elements by either plotting the image or printing the text. Now that we've got our sample elements ready, let's run the second part of our document processing pipeline and populate our Vectorstore. To do this, we implement this simple function which loops over our set of elements. For textual elements, it simply upserts the corresponding text. For visual elements, it first runs the image description chain, then upserts the generated text along with the base 64 string as metadata. We now run this function on our set of document elements and get the corresponding IDs as a confirmation that all of our data was upserted successfully to the Vectorstore. In the previous video, we built the document processing pipeline and ran it on a few examples. Today, we're going to build the chain components of the inference pipeline using the Langchain LCEL framework. As explained in the first episode of this series, we will build and compare 2 different pipelines for the question answering phase. Both pipelines will make use of the retriever component and the QA component with the addition of the VQA or visual question answering component for the first pipeline, And finally, both will use the synthesis component. In total, we have 4 elements to build, namely the retriever, QA, VQA, and synthesis chains. So without further ado, let's get started. So the first component we'll build is the retriever. It's also the easiest one, as we only need to turn our vector store into a retriever. So we take the Qdrant Vectorstore we created earlier, use the asRetriever method, and specify the top K parameter. Let's set it to 4. This means our retriever will find the 4 most relevant chunks to the user query. Let's now test our retriever. In the last episode, we populated our vector store with elements from the recent Qdrant paper. So let's ask, for example, how well does Qdrant perform against competitors? This function allows us to display the retrieved elements in order by either printing if it's text or plotting if it's an image. And here are the elements that were returned by our retriever. We can see that the first element is a chart comparing Qdrant's performance against other models on 2 different benchmarks. The second, third, and fourth elements are all paragraphs which at some point mention the performance of Qdrant compared to its competitors. Now that we have confirmed that our retriever works as expected, returning both images and text by order of relevance to the question, we can move on to the second component. So again, we will first create the question answering chain and then test it on a sample query. Just like the description chain which we saw in the last video, you can see that it's a simple chain composed of a prompt, a model, and an output parser. The prompt starts with a classic system instruction followed by a more detailed user instruction. We specify that this is a question answering setting that is based on provided context, and that we want direct, concise, and short full sentences to limit the unnecessary verbosity of the model. More importantly, and this is critical for RAG settings, we make sure the model doesn't try to invent information or use his own knowledge if the context isn't enough to answer the question. This allows us to limit hallucination effects and thereby keep LLM interactions stable and robust. We will see in future videos how we can build a sourced QA chain where the LLM points us to the exact source of each part of the answer, specifying which document, page, and paragraph it got the information from. Finally, we insert the question, the context, and an empty answer that the model is supposed to fill. Let's now test our QA chain. So we ask the model if Qdrant is open source and if so, under what license. As the Qdrant paper was published only a few weeks ago, the model isn't supposed to know about it. So we also give it some context from the document stating that Qdrant is published under the Apache 2.0 license. As specified in the prompt, the model gives a short, direct, and concise full sentence answering the question based on the given context. Let's now build our third component, the VQA chain. Similarly, we will first create the chain, then test it on a sample query. Once again, we have the simple prompt model parser structure. We start with a classic system prompt, then a first user message specifying that this is a VQA task, that we want direct, concise, and short answers, and that the model should simply say no information if the given image is not enough to answer the query. Finally, the second user message provides the image as a base 64 URL. Let's now test our VQA chain on a simple example. This time the question is, what is the head dimension for the decoder of the model? The image we will give is the third element we extracted from the Qdrant paper, which is this table. And as you can see, for the decoder model here the head dimension is 128, which is the expected answer for our query. And as required by the prompt, the chain yields a direct and concise answer stating that the head dimension for the decoder of our model is 128. Keep in mind that this VQA task is very different from the image description task we saw in the previous video. Just like for textual tasks, different models can be relatively stronger or weaker on image description or VQA. Having the right model for the right task, or in our case as we will see in the next video, the right pipeline for your model, is a key point you should pay attention to when building your generative AI apps. And finally, let's build our fourth and last component, the synthesis chain. Again, same structure, prompt model parser. This time we instruct the model to answer a question by combining and synthesizing a set of partial answers or answer attempts. If all the given answers are not enough to give a final answer, the model should just say, "I don't know." And finally, we insert the question and the set of answers in the user prompt. Let's now test our synthesis chain. So we have 3 answers based on 3 different chunks or elements to the same question. The first answer attempt successfully finds the information in the chunk. The second and third attempts don't find any relevant information and therefore return a negative message. We now call our synthesis chain by providing the question, which is again what is the head dimension for the pixtral decoder, and inserting the 3 answer attempts separated by line breaks. As expected, the model simply discards the failed answer attempts and uses the information from the successful one to provide a final answer. Now that we have built our 4 main components, we will see in the next and final episode of this series how we can connect and chain them all together to form our 2 inference pipelines and compare their performances. In the previous video, we implemented the individual building blocks of our inference pipeline, namely, the retriever, QA, VQA, and synthesis chains. Today we will see how to connect and chain them together to obtain the full inference pipeline and run it end-to-end from the user query to the final answer. It will be the occasion to present and use some of the most important LCEL building blocks, namely, the runnable pass-through, the runnable branch, the runnable lambda, the assign method, and the map method. We will take some time to explain each of them as we will be encountering them a lot in future videos. So the first step of the pipeline is to get the relevant documents to the query using our retriever. As we're building our pipeline using the Langchain LCEL framework, we need to set up our input-output structure in the form of dictionaries following the piping logic. You can check out our previous video on the subject to quickly get up to speed with Langchain LCEL. The input of our pipeline will be a simple dictionary containing the user query. And as you can see, the output of the retriever chain is a dictionary containing both the question, which is simply reinserted without change using the runnable pass-through base component, and the relevant documents which are obtained using our retriever component. In other words, the input here is the question. The runnable pass-through applied to the input simply yields the same input. The retriever applied to the input yields the relevant documents. Now this dictionary containing the question and the documents will be the input for the next step. The second step is to split this dictionary into multiple dictionaries, each containing just one document. The goal is to have multiple question single chunk pairs that will each be processed by an LLM to produce a partial answer. We obtain this using 2 different functions depending on the pipeline we're building. For the first pipeline, we want to separate the documents into textual chunks and visual chunks. We therefore condition on the type which is present in the metadata of the retrieved vectors. If the type is textual, we create a dictionary containing the question and the text content of the retrieved document. If the type is visual, we create a dictionary containing the question and the base 64 encoding of the image, which we get from the metadata. This way, we obtain a list of dictionaries, each containing either a question and a chunk of text, or a question and an image. For the second pipeline, we don't use visual question answering. We therefore only need to separate into dictionaries containing a question and a chunk of text. For visual chunks, the text simply corresponds to the generated description of the image. As you can see, this second step corresponds to this part of the pipeline, connecting the retriever to the QA and VQA components. It does that by spreading the retrieved results so they can be processed in parallel by either the QA-VQA module or the QA module alone. So far, we have implemented the piping logic for the retrieval of chunks and the splitting logic to obtain multiple question chunk pairs. We will now implement the conditional logic in order to treat the input pair differently based on the type of chunk. We do that using the runnable branch. The runnable branch is made of 3 main components: a condition function, a positive runnable, and a negative runnable. The condition function is simply a function of the input elements which returns a Boolean value. In our case, it returns true if the input type is visual, and false otherwise. The positive runnable is the runnable which will be used on the input if the condition function returns true. In our case, it's the VQA chain. And naturally, the negative runnable will be used on the input if the condition function returns false, meaning that the input type is textual. In our case, it's the QA chain. Now this entire construct will behave like a single runnable when we pass input to it. If the input is visual, it will behave exactly like the VQA chain. And if the input is textual, it will behave exactly like the QA chain. If you're wondering where this type attribute came from, it was added to our question chunk dictionaries when we performed the splitting in the last step. Once the separated chunks are processed in parallel, we will need to concatenate the results before sending them to the synthesis chain. We do this using this simple runnable lambda. The runnable lambda is the simplest way to turn any function into a runnable that can be chained with other runnables. As you can see here, we define a lambda function which takes as input the list of string answers we get from the QA and VQA chains. This function simply concatenates those answers, separating them with line breaks and a set of dashes. If you remember the prompts from the previous episode, we specifically instructed the QA and VQA chains to say, "No information," when the provided chunk is irrelevant or not enough to answer the question. We therefore filter out those instances by adding this if statement here, so we only keep the actual answers generated by the QA and VQA chains. Finally, let's chain everything together to produce the final answer. To do that, we will use all the components and connectors we have implemented so far to build our two inference pipelines. But before we do that, we need to introduce our two last building blocks, the assign method and the map method. The assign method is usually used together with the runnable pass-through in order to store the results of a chain in a new attribute which is added to the input dictionary. For example, if the input is a dictionary containing a question and a set of documents, the output of this pass-through.assign module will be a dictionary that looks like this. As you can see, the question and the documents are simply passed through to the output without change. A new attribute called answer is added, and this new attribute contains the result of this chain applied to the input dictionary. Let's now talk about the runnable.map method. So in our case, as explained earlier, we want to send multiple inputs in parallel to our question answering module. Each input is comprised of a question and a retrieved chunk, which is either textual or visual. The QA-VQA module takes in this input and returns a string answer. In Langchain LCEL, we can use the batch method to send in a list of inputs which will be processed in parallel by the module. However, what we want is to chain the whole pipeline into a single runnable and simply call the invoke method on the whole thing. This is where the map method comes in handy. When we call the map method on a runnable, it creates a new object called the runnable each. The advantage of the runnable each is that it takes as input a list of dictionaries, implicitly calls the batch method to process them in parallel, and returns the list of outputs. In other words, wrapping your chain in a runnable each object and calling the invoke method is equivalent to directly calling the batch method on your chain. Now that we have introduced all the building blocks we needed, we can finally implement our entire inference pipelines as two single LCEL runnables. Let's start with the first pipeline. So the input of the pipeline will always be a single question. First, this question goes through the retrieval chain. This chain yields a dictionary containing the question and the list of retrieved chunks. This dictionary then goes through this whole module whose role is to generate the list of partial answers corresponding to each chunk. The chain at the core of this module is composed of three steps. First, the separator splits the dictionary into a list of dictionaries, each containing the question, a single chunk, and the type, textual or visual. This list then goes through the branch runnable, which sends each dictionary either to the QA chain or to the VQA chain depending on the type. Here we use the map method on the branch runnable in order to process the list of inputs in parallel. Finally, the generated answers are all concatenated with a set of dashes and line breaks to delimit them. Now the result of this three-step chain, which is a single string containing the concatenated answers, is stored in this answers attribute and added to the initial dictionary using the runnable pass-through.assign method. And finally, this dictionary containing the initial question and the answers string is fed to the synthesis chain which generates the final answer. The second pipeline is pretty much the same. We first go through the retrieval chain, then generate the answer string with this three-step chain. The main difference is that the separator here doesn't split into textual and visual chunks. It splits into a list of textual chunks where the images are replaced by their textual description. Naturally, instead of mapping the branch runnable, we only need to map the QA chain since all our inputs are textual now. And the rest of the pipeline is exactly the same. We concatenate into a single string, assign it to the answers attribute, and pass the whole thing to the synthesis chain. Now what you see here is the literal implementation of the charts we saw in the first episode. From the retrieval to the splitting and branching into QA or VQA, processing in parallel and concatenating, to the final synthesis step. And the same goes for the second pipeline, with the crucial difference that we perform textual QA on the descriptions of images instead of performing visual QA on the raw images. Let's now test and compare our two pipelines using a sample query. Let's start by seeing how our first pipeline responds to the question, what is the number of KV heads for the encoder in the textual architecture? So we know that the answer to this question can be found in this table, which is one of the sample chunks we've upserted to our vector store. Specifically, since we're asking about the encoder architecture, the number of KV heads here would be 16. Let's now see how this first pipeline responds. So the final answer we get here is, I don't know, apparently due to inconsistencies found in the partial answers. If we do the same with the second pipeline, we immediately get the correct answer, which is that the textual architecture includes 16 KV heads for the encoder. So how can we explain this difference in performance? The only difference between the two pipelines is that the first uses visual question answering on raw images, while the second first generates textual descriptions of the images, then uses textual question answering on those descriptions. The second pipeline performs better here for two main reasons. First, it's almost always a good idea to break down your LLM tasks into smaller, more manageable subtasks. Here the task of answering a question from an image was broken down into first describing the image, then answering the question based on the description. Second, it actually all depends on the model or group of models you use in your pipeline. In our case, for the sake of simplicity, we used the same model for both the image description task and the VQA task. If you recall from the first episode, it was the Mini CPM which we deployed locally using LM Studio. Mini CPM version 2.6 is based on the Qwen 2.7b model and surpasses state-of-the-art models like GPT-4o and Gemini Pro on single image understanding, which means that in our case, we've simply used a model which is far better at image description than at direct VQA. The key takeaways from this quick tutorial are therefore, number 1, a robust pipeline is a pipeline where LLMs only perform very simple atomic tasks, and number 2, there is no best pipeline. It all depends on the models you have at your disposal, with their unique strengths and weaknesses. And that's it for our Multimodal RAG series. In a future series also dedicated to Multimodal RAG, we will explore the usage of specialized models for specific tasks like chart understanding, table understanding, and so on. If you appreciate the content, make sure you like and subscribe to the channel. See you soon for more tutorials. Bye-bye.